Valence bond theory. So the Lewis model is an oversimplification. And it does not explain some things that need to be explained. And so there are more advanced bonding theories that use quantum mechanics and apply those ideas to molecules. And so there are quantitative approaches which deal with numbers, and they predict bond length and bond strength, molecular geometries, dipole moments, all that stuff. It involves a lot of math, and we're not going there. Okay? So we're going to look at the qualitative aspects of two of these more advanced theories, and one of them is valence bond theory. So valence bond theory treats chemical bonds as the overlap of orbitals. So just a little review. Electrons occupy quantum mechanical orbitals that are localized on individual atoms. So we've got S, P, D, and F atomic orbitals that we've learned about. There are also something called hybridized atomic orbitals. And a hybridized orbital is just going to take two or more of these standard orbitals and mash them together and form a hybrid. So when two atoms approach each other, the electrons and nucleus of one atom are going to interact with those of the other atom. And valence bond theory is going to look at the energy changes that result from those interactions. A chemical bond will form if the energy of the system is lowered by the interaction. So here's a picture. So if we look at two hydrogen atoms coming together, and this is a graph of energy. Okay, so energy is high and energy is low, and we're looking for this low spot. As these atoms come closer together, their energy decreases, and their orbitals are going to overlap a little bit, and it decreases, and when they get this close together, they're at a minimum energy. And if you squeeze them closer together, the energy goes back up. And so, you think about a ball rolling down a hill. Where's it going to stop? It's going to stop down here. Lowest energy. So at this point, at this distance, these two atoms have the lowest energy. And so that's the chemical bond. And the amount of energy here would correspond to the energy of the bond, and the distance, this is relative distance between the hydrogen atoms, this would be the bond length. And at that particular distance apart, that's the most stable for those two atoms. They're more stable there than if they're separated farther. So the potential energy of the two hydrogen atoms is lowest when they're separated by a distance that allows their 1s orbitals a substantial degree of overlap without too much repulsion between their nuclei. That distance is the bond length of the H2 molecule. So we have their orbitals overlapping, but if we squeeze them too close, then we get repulsion between the positively charged nuclei. So the interaction energy is usually negative, meaning it's stabilizing, when the interacting atomic orbitals contain two electrons that can spin pair or orient with opposing spins. So if you've got two half-filled orbitals coming in, they each have one electron. If those electrons spin pair, then we've got two electrons in those overlapping orbitals, and that's a more stable situation. Usually the electrons come from two half-filled orbitals, but sometimes you have two electrons from a filled orbital overlapping with an empty orbital from another atom, and that's called a coordinate covalent bond. So instead of each atom bringing one electron to share to the bond, you have a poor atom who doesn't have any electrons to share, and another very generous atom who has two electrons, and he's like, oh, well, you can't give me anything, but here, I'll share my two electrons with you. That's a coordinate covalent bond. When those two atoms with the half-filled orbitals approach, the orbitals overlap, and the electrons will align with opposite spins. They will pair. They can switch their spins. And so if they came in parallel spin, one of them will switch, and they'll have opposite spins, and they'll pair up that way. So the valence electrons of atoms are in these quantum mechanical orbitals, and it's still the valence electrons that are doing this. These are the electrons that are on the outside of the atom, because that highest quantum number, those are the largest orbitals, and those are the ones that are going to be on the outside, and they'll interact first with a neighboring atom. The chemical bond results from the overlap of two orbitals, generally two half-filled orbitals, and those two electrons pair up and occupy the orbital. The geometry of the overlapping orbitals is going to determine the shape of the molecule. So let's look at some examples, because that probably didn't make a whole lot of sense. Let's make sure I didn't skip anything. So let's look at this molecule, dihydrogen sulfide. So here we have a hydrogen atom. Its electron configuration is very simple. These are orbital diagrams. It has one electron. It'll be in the 1s orbital. Another hydrogen atom, one electron in the 1s orbital. And here's sulfur. We're just looking at valence electrons. So sulfur has 6 valence electrons, and they will occupy the 3s and the 3p orbitals. So the 3s will be full. One of the 3p orbitals will have a pair of electrons, but there will be 2 half-filled p orbitals. And what valence bond theory says is that this half-filled orbital is going to overlap with this one, and those electrons will spin pair. And this other orbital will overlap with this one, and those will spin pair. These are the p orbitals, and here they're represented in red. The p orbitals, there was one that went up and down, and then there were 2 that went across. All 3 of them are perpendicular in 3-dimensional space. So here we have one of those p orbitals overlapping with the hydrogen, and there's the pair of electrons, one from sulfur, one from hydrogen. And here we have hydrogen with another p orbital, and there's the pair of electrons, one from sulfur, one from hydrogen. And then sulfur also has this s orbital and another p orbital. Remember, both lobes are the same orbital. So all 3 of these orbitals now are full. Well, the actual bond angle of this bond is 92 degrees. Valence bond theory predicts that it would be 90 degrees, so that's pretty close. Vesper theory predicts 109.5, because let's look at that real quick. If we look at the Lewis structure for this molecule, it's a lot like water, isn't it? Here we have sulfur with 4 electron groups, and Vesper theory predicts that the bond angle between hydrogen, sulfur, and hydrogen would be less than 109.5. That these 4 groups would form a tetrahedral electron geometry. There are 2 lone pairs, which means that the molecular geometry is bent, and those lone pairs would force these 2 a little closer together. So Vesper theory predicts less than 109.5. Well, is 92 less than 109.5? Yeah, but it's probably a bigger difference than we would expect just from those 2 lone pairs. Any questions yet? So the bond overlap thing works okay for that molecule. It doesn't work real well for some other molecules, for lots of other molecules, in fact. If we look at carbon and hydrogen. So here's carbon's valence orbital diagram. We've got 2 electrons in the 2s, and then we've got 2 more electrons, and they each have their own p orbital. And here's hydrogen again. And so what this would predict is that this electron from hydrogen would overlap with one of these p orbitals, and we would get this bond here, and then we'd have another hydrogen that would overlap with this one, and that we would end up with something like this, with 2 hydrogens and a carbon. Just from overlapping half-filled orbitals, that's what would be predicted, because carbon has 2 half-filled orbitals. But in actuality, that's not what happens. Carbon and hydrogen are going to form methane. There's going to be 4 hydrogens, and there will be 109.5 degree angles around that carbon, not a 90 degree angle that would be predicted by these p orbitals. So we need something else in this theory, because this is not explaining reality, so that's not good. Well, so far we've been assuming that the orbitals in a molecule are the same as the orbitals in an atom. But when atoms join together to become a molecule, what happens is that their orbitals change. You think about 2 people getting married, and just kind of out of necessity, some of their habits have to change, right? And so being in this bonded relationship now, things have to change. So the molecular orbitals are a little different than the standard atomic orbitals, and we call them hybrid orbitals. So hybridization is just a mathematical procedure in which we combine standard atomic orbitals and we form hybrid orbitals, and we're not going to get into the math of that. But these correspond more closely to the actual distribution of electrons in the molecules. They're still localized in the atoms, but they've got different shapes and energies. So how does this work? The hybrid orbitals are going to minimize the energy of the molecule by maximizing the overlap between the orbitals. So they're going to provide greater orbital, the hybrid orbitals provide greater overlap because the electron probability density is more concentrated in a single direction instead of like the s orbital and being spread all over the place. Even a p orbital has 2 lobes. When you have just a regular standard atomic orbital for p, it's got equal densities on each lobe. When you hybridize it, you make one of those lobes larger. Hybridization does require energy, so it requires an energy investment. So it'll only happen if you get enough payback by actually making the bond. And so we're going to look at the interior atoms and their hybridization, and we're going to pretend that the terminal atoms don't hybridize. And we do find that atoms that form more bonds are more likely to hybridize. So like things with hydrogen, this really doesn't hybridize much. So some general statements, and then we'll look at specifics. However many standard orbitals you add together, you're going to get the same number of hybrid orbitals. So if you put 3 standard orbitals together, you'll get 3 hybrid orbitals. The combinations that you add together are going to determine the shape and energies of the hybrids that you get out. And the one that occurs, the particular combination of hybridization that occurs is the one that's going to give you the lowest energy. So there's all kinds of calculations that could be done, and that's beyond, way, way beyond the scope of this class. I don't even enjoy that stuff much. So what we're going to do is we're going to use Vesper theory electron geometries to help us predict hybridization. So it's a very qualitative description of this, but it's good enough and it works. So one hybridization is taking 1 s orbital and 3 p orbitals. So for example, carbon. Here's the orbital, standard orbitals for carbon, atomic orbitals. It has 4 valence electrons, and it's got 2 in the 2s, and then 1 each in these 2p. So that's what carbon is when it's all by itself. But carbon hybridizes. And so what it does is it takes these 3 orbitals and it combines them all together and makes 3 identical orbitals out of them. They're all going to have the same energy. They're going to have the same shape. They'll just be oriented in space differently. And so we call this an sp3 hybrid because it's made of 1s and 3p orbitals. We started with 4 orbitals. We end up with 4 orbitals. We say the hybrid orbitals are degenerate, meaning they're the same energy. So S was lower in energy and P was higher in energy. And when we put these all together, those sp3 hybrid orbitals are between the two. So the energy of the orbitals changes. So here are pictures of the standard atomic orbitals. There's the s orbital and the 3 p orbitals. And when we put these together mathematically, we end up with these 4 guys. This looks a lot like a turkey drumstick or something, or maybe a bowling pin. I guess it depends on how hungry you are. My lunch wasn't big enough. It looks like a turkey drumstick. But the combination of these, the combination of these 4 orbitals gives us 4 identical orbitals in terms of energy and shape. The just difference is how they're arranged. And so if we put them all together, do you recognize that shape? That's that tetrahedron we've been talking about. So these 4 are going to point to the corners of a tetrahedron. Now they do have this little lobe on the back, and when we draw them all together, we tend to just ignore that because it makes the drawing really, really complicated. But they do have a second lobe over here, but this one's much bigger. See how it's lopsided now compared to the P? So that's the sp3 hybrid orbital. So when we take carbon and we hybridize its orbitals, now we have 4 identical orbitals, hybrid orbitals, and those are going to have carbon's 4 valence electrons in them. And so each valence electron gets its own orbital. Those are all going to have parallel spins. And now these 4 orbitals can overlap with hydrogen, and we see that we'll have 1, 2, 3, 4 to overlap with 1, 2, 3. Hello, pointer. There you go. 1, 2, 3, 4 hydrogens. And this gives us that tetrahedral shape. Just looking at standard atomic orbitals overlapping doesn't give us the tetrahedral shape, but hybridizing them does. So the geometry now agrees with experimental observations. So that tells us this theory is better than without the hybridization. Is this making some sense? Good. This is, I took chemistry as a senior in high school. I took honors chemistry, and I got an A in the class, but I often felt like I didn't know why I was getting the answers right. I really felt like I didn't understand. And this is one of those things that I distinctly remember sitting in class, in the periodic table, the front of the classroom, and Mr. Floyd Sturdivant going on and on and on about sp3 and carbon, and it just never made any sense to me in high school. Now, the next time I took chemistry in college, then it started to make sense. But, I just remember this being just really confusing. It was probably me, but maybe it was him. I don't know. Anyway, so if this is confusing, you have my sympathies. But please ask questions. Mm-hmm. By hybridizing, their energy gets lower because when they can make these bonds. So hybridizing requires energy, but then when they make these bonds, they get a payback. So it's a little bit like making an investment. If you want to get into the real estate market, because you can, make money renting properties, right? But you have to put money in first. But you don't put money in if the amount of money that you're going to get back is less, because that would be dumb, right? Of course, people do it all the time, but anyway. That can't happen in this real estate market. So it requires an investment to make these hybrid orbitals, but then there's a big payback when these bonds form. Yes?
So we can't make the bond without the hybrids? Or just enforces them?
So the question is, it can't make these bonds without the hybrid orbitals? We observe that it does not make the bonds as straight atomic orbitals. So if we go back to this guy, Where is he? There he is. If we look at just overlapping standard atomic orbitals, this is what we would get. We would get CH2, and it would have a bond angle of 90 degrees. We observe that that does not happen. Okay. Would there be energy released when this bond forms? Yes, there would. But it just doesn't happen that way. So some of this is, we come up with an idea, and then we predict what's going to happen, and we look at experimental observation, and if those don't match up, then we have to fix our theory. And so I will often personify atoms and stuff, which can help us remember things, but it can be a little misleading at times too. This matches up with observation. We do know that when the bond is formed, energy is released. We know that in order to form these hybrid orbitals, there is energy expended. It requires energy to do that. One way to think about it, bless you, is that here there are 4 bonds being formed. Each of those bonds releases energy. In the other idea, we only had 2 bonds being formed. So this is going to be twice as much energy being released. Does that help at all? Kind of? Yeah. It's hard to understand. And one of the hard things is, in general chemistry, we have to lie to you to a certain extent. Because if your 5-year-old asks you to buy a $500 bike he saw on TV, and, you cannot thoroughly explain economics to him to explain why you can't buy him that bike right now. He doesn't understand that, yes, you have the money in the bank, but it's earmarked for other things, and you just can't go into it because he's not going to get it, right? And so some of this, you guys have questions, and they're good questions, but the real satisfying answer is way beyond this class. And it requires just a lot more chemistry and more journeys into physics. So some of it you just have to say, well, that's how it is. And just, don't give up on those questions, but, just set them aside. I'd like to know the answer to this. I can't really get the answer to this right now. So that's kind of how life is. Let's look at what happens with a lone pair. If we look at ammonia, NH and H3, the bond angles here, by observation, are 107 degrees, which is closer to an unhybridized bond angle of 90. The presence of that lone pair reduces the tendency to hybridize. But ammonia does contain hybrid orbitals, and so we get this tetrahedral shape by combining the s and 3p orbitals from nitrogen. Let's just look real quick at the orbital diagram for nitrogen. Nitrogen has, I don't want that one. It's got the 2s and the 2p, right? Those are its valence electrons. So it's going to have 2 in there, 1, 2, 3, 4, 5. So when this hybridizes into, it's going to make 4 orbitals that are sp3. One of them has a lone pair, is already full. But the remaining 3 can overlap with hydrogen and form bonds. And so that's what it will do. Question?
No, that was
Oh, good. What about double bonds? What are we looking at here? Well, we don't have to hybridize all of the p orbitals. What if we take a 2s orbital and just 2 of the 2p orbitals and hybridize those. Then we end up with sp2. It's an s and 2p orbitals hybridized. And because we started with 3, we'll end up with 3. And then this unhybridized p orbital just remains unchanged. So we took these guys in the box and we hybridized them. You can think of it as averaging, if you like. That helps you. And so they're going to be intermediate in energy between the originals, and this guy's going to be the same. So now we have sp2 hybrid orbitals, and we've got this extra p orbital that's left over. Well, what does that look like? Well, when we take an s and 2 p's and throw them all together in the mixer, we end up with these turkey drumsticks again, but the orientation is different. They're going to make a trigonal planar structure. They're going to be flat because one of those p orbitals got left out. So the other p orbital is going to be perpendicular to these guys. So if we look at H2CO, let me just throw in a quick Lewis structure. Now, we are only looking at hybridizing the central atom, just to keep things simple. But here we have carbon with 2s2, 2p2. Here's the oxygen. Oxygen has 6 valence electrons. It's got 2 half-filled orbitals here. And here we've got hydrogen. So what carbon will do is it will hybridize the 2s and these 2p orbitals that are half full, and it'll make sp2 hybrid orbitals, and the extra electron, the 4th electron, will go into this unhybridized p orbital. And I imagine some of you are thinking, why would you even think of doing that? Why would it do that? Well, it's just because people have observed stuff and they thought about it for a really long time, and I wouldn't expect that to occur to you to try to do that.
But does that only happen when there's an orbital that's unoccupied to begin with?
Does an unhybridized orbital get left out only if it's empty? Is that what you're asking? Did this guy get left out of the hybridization just because he was empty? No. No. Yeah. So let's look at what happens. Here's the carbon. There's the sp2 hybrid orbitals. Okay, they made that trigonal planar shape, and each of those can make a single bond with another atom. So these two are going to overlap with the hydrogen's 1s orbital and form a bond, and this guy is going to overlap with one of those half-filled orbitals on the oxygen and form a bond. These are called sigma bonds. Sigma bonds are what's a good way to describe that? It's gone. It's gone. This end-to-end overlap of bonds is a sigma bond. Now, what happens with that unhybridized p orbital? Well, that guy's up and down here. And oxygen also has oxygen's orbitals, we're assuming, are unhybridized. So it's got this vertical one here, and this one, it also has another one going at an angle that we didn't draw because it got messy. So we've got this vertical one. This is half-filled, and this one's half-filled, and what they're going to do is they're going to overlap side to side. Both lobes are the same orbital, and so these two lobes will overlap, and these two lobes will overlap. And in that overlap, there will be one pair of electrons.
So the two lobes create one huge orbital.
The two lobes overlapping create this, it looks like a triple bond, doesn't it? It's not a triple bond.
It looks like, but the one bond, and then it looks like another bond if it's just looping around.
Yeah, you can kind of think of it as looping around, but it is this part on the top and this part on the bottom. Remember, they have nodes. And the electrons, you're like, well, how can it be in this part and that part when there's no way for it to get through? Well, they act like waves and particles, and they can be here and they can be there, and they can go. It's very confusing, isn't it? But we just have to remember, oh, that's right, electrons don't have to act the way we think they should. So this is forming the second bond. Both of these sections are just one bond, one pair of electrons, and this is the sigma bond in the middle. So this is called a pi bond, and these are sigma bonds. So this is a sigma bond, and that's a sigma bond, and this is a sigma bond.
So even though the double bonds kind of occupy similar space, they're separate orbitals?
Yeah, these two bonds are occupying separate spaces. So this one is like overlapping, kind of going over and under, and this one's going straight through. But they're not running into each other. This orbital is not overlapping with this one at all. They're distinct. So we got this overlapping, and then these guys are overlapping, up here and down here at the same time. So pi bond happens when the p orbitals overlap side to side. So here we have a p orbital and a p orbital, and they're side to side. The tops overlap. Let's do it this way. So this part overlaps and this part overlaps, is what's happening. A sigma bond is where they run into each other end to end. So end to end is a sigma bond, and if you were to look at a sigma bond from the end, it would look spherical. If I was going to take this and stand at this end and look down the axis, it would be spherical. And the sigma letter looks like an O, doesn't it? This one, if I looked at it from the end, it would look a lot like a pi orbital, because there'd be this piece on the top and the piece on the bottom. That's looking from the end, standing here and looking that way. Okay? Does that help a little bit? So we can label these. You're like, nah, we don't want to label them. Yeah, we're going to label them. So here in the labeling, they're saying this is a pi bond, which is describing the type of overlap side to side. And this is overlapping a p orbital from carbon with a p orbital from oxygen. Those are not hybridized. This is a sigma bond. So we've got sigma, and from the carbon, it's an sp2 hybridized orbital. That's these purple guys. Remember, we took one s and two p orbitals, and we mashed them together and got 3 new orbitals. And that's overlapping with an unhybridized p orbital from the oxygen. These two bonds are the same kind of bond. They're both sigma bonds between a carbon sp2 hybrid and a hydrogen unhybridized s orbital. So that's one way to label them. And you should be able to identify what kind of bonds these are and what kind of orbitals are being involved.
Just by looking at the rules.
Well, certainly from looking at a picture like this at this point. So we're getting more insight from this valence bond theory than from the Lewis model. Because that double bond between carbon and oxygen is actually 2 different kinds of bonds. It's not 2 identical bonds. When we have a double bond in the Lewis model, when we talk about that in valence bond theory, it's always going to be 1 sigma bond and 1 pi bond. The pi bonds are weaker because the overlap is not as strong. That side-to-side overlap is not as efficient as the end-to-end. So that pi bond is weaker than the sigma bond. So if you're going to break one of the bonds, it's the pi bond that will break first. because it's weaker. And the sigma bond would break last.
What's the bond between the hydrogen and carbon bonds?
The bond between the hydrogen and the carbon is a sigma bond.
It's an extension of the other sigma
Right.
then?
Now let's go back to this guy. So this carbon has the sp2 hybrids. Those are the purple lobes here. These 3 hybrid orbitals. And these overlap with hydrogen. And they're overlapping the end of this orbital. You can't really talk about the end of an s orbital. S orbitals can only form sigma bonds. They can't form pi bonds because they don't have these 2 lobes to overlap side to side. So this is a sigma bond. It's the end of this sp2 overlapping with the hydrogen.
Okay.
And this is a sigma bond, and then this is a sigma bond. These are good questions because you got to get it straight. It's not going to just suddenly come to you in the middle of the night. This is not one of those things.
So even though it's not part of the double bond, it's still, all 3 of them are still sigma.
Yes. So there's a single bond and a single bond, and this is a single bond, and this is another bond. They just happen to be between the same 2 elements, and so that's what makes it a double bond. There's 2 bonds there. The 4 electrons that are being shared are not being shared all together. They're being shared in 2 separate groups. One in this pi and one in this sigma.
So the double bond between carbon and oxygen collectively is stronger than a single bond. But
Yes.
separately, there's one.
Yes, collectively, this double bond is stronger than a single bond. But within this double bond, these two bonds are not equal in strength. The sigma bond is stronger than this one. But this just adds to the strength of the bond between carbon and oxygen and causes them to pull closer together. If you got rid of this, then this bond would be similar to these other single bonds. So, single bonds can rotate. If we look at this molecule, and here we have, here's this carbon, and it's got 4 purple orbitals here. What would the hybridization of that be? The geometry is tetrahedral, sp3. So, I mean, how can you get 4? You have to combine 4. So, to get 4 orbitals, it's got to be sp3. 1 s and 3 p's. And so we're getting these 4 purple orbitals here. And they are arranged in a tetrahedral shape. And here we have a sigma bond with hydrogen, and another sigma bond with hydrogen, and here's a sigma bond with chlorine. So that's this carbon here, hydrogen, hydrogen, chlorine. And then the 4th orbital is going to form a sigma bond with the other carbon, which is very much like this one, with 2 hydrogens and 1 chlorine. So both of these carbons are sp3 hybridized to make 4 identical orbitals. And they're making sigma bonds with 4 different things. Well, this bond, there is rotation. There's nothing to keep this from rotating. And so we could take this end of the molecule and, let's see, try to follow that circle. And we could spin this around this way, and we could spin this one around that way, and you can just twist them around. And they're not going to unscrew or anything. They swivel on each other. When we have a pi bond, now we can't have any rotation because we've got this overlap at the top and the bottom, and then we've got this thing in the middle. And it's a little bit like when you put your 2 index fingers together and you can rotate your hands with your fingers still touching. But if you put 2 fingers from each hand together, now you can't rotate, right? I can't spin this, it just doesn't work. Because there's that second thing in there. Yes?
So the 2 carbons, if they're bonding together, how does the previous going into polarization
Mm-hmm.
Because to me, I look at them, they should be off or same polarization, and yet they're attaching, they're bonding there, so it's just a covalent sharing.
This is covalent sharing of electrons, yes. So here, this carbon is sp2 hybridized, and it has this one p orbital that's unhybridized. Same thing over here. A p orbital will overlap, forming a pi bond, and then we have the sigma bond between the sp2 and the sp2. And because of the nature of the pi bond, you can't have rotation. And so those are stuck in a configuration. And when we look at just a structure here, the single bond, think of that as like a single axle, and you can spin this guy around. And so if you've got the chlorine on the bottom or the chlorine on the top, it's really the same molecule because it can spin like that. When you put this double bond in here, that's like two sticks attaching these two together, and they won't rotate anymore. And so we have this molecule, but if we draw it this other way, I'm probably getting ahead of myself, but I can't help it. Trans, yes, cis and trans. So this guy is actually different than this because there's no rotation. It's a bad double bond. There's no rotation here. And so I can't just swivel this around and get the chlorine to be in this position. Over here, if I drew, where can I draw it? Right here in the middle maybe. If I drew it like this, it doesn't matter. It'll twist around. I can just twist this end around until both of the chlorines get together. This one you can't twist around. And so this is actually different than that. The only way you can get from one to the other is by breaking that pi bond. So that's an important concept, is that double bonds can't rotate. Single bonds can. Oh yeah, see, I got ahead of myself.
Does that make it a different molecule that have them separated?
Yeah, these are different molecules, and they have slightly different properties. They're isomers of each other. They've got the same number of atoms of each element, but they're connected a little bit differently. So with the single bond, we've got free rotation. Here's the space-filling model, and this guy can just spin around as needed to get to different arrangements. Here with the double bond, you cannot rotate at this carbon-carbon bond. And so they're either together or they're on opposite sides. It's two distinct forms.
Just like your analogy of parties and people. If you're single, you're allowed to roam around. If you're not, you're stuck with your parents.
Very good. I like that. The single bond, they can rotate and mingle, and the double bond, you're in a pair, you're in a relationship, you're stuck with the person. That's good. I like that. Yeah. Well, yeah, we just have to exclude San Francisco from all of our discussions. Okay, so sp hybridization. So we've looked at one S with 3 Ps and one S with 2 Ps, and now we're going to look at one S and 1 P. And let's see, Andrew would be laughing his head off right now. You're talking about P. Sorry, yeah, mother of a 5-year-old. Okay, so when we combine these, we get 2 degenerate orbitals. They're called sp. Again, we don't write the ones because chemists don't write ones, right? You see a pattern there? It's just sp. It's not sp1. It's just sp. And what's left are 2 unhybridized p orbitals. So if we put these 2 together, then we get 2 turkey drumsticks, and they're going to be opposite from each other. Now that kind of looks like a a p orbital, doesn't it? But this is actually 2 orbitals. Each of them has this little lobe on the other side that we're just kind of ignoring for convenience sake. But these are perpendicular. And so those are going to be arranged in a linear geometry across from each other. So let's look at acetylene. It says draw the Lewis structure for acetylene. So here we've got we can cheat a little bit because it's showing us there's a triple bond. So we'll put the triple bond in there, and then let's see if we have enough electrons. Well, hydrogen brought 1, so that's one end here, and then carbon brought 1, 2, 3, 4, and this carbon brought 1, 2, 3, 4, and that hydrogen brought 1. So we've got all of our cookies accounted for, all of our electrons. So we don't have any lone pairs or anything. And looking just at Lewis theory, we'd look at this carbon and say, oh, it's got 2 electron groups. We would predict that its geometry is linear, right? No lone pairs. Well, let's look at what happens with the hybrid orbitals. So here we've got hydrogen, and here we've got the carbon. And what the carbon can do is it's always going to bump this electron up to an unfilled orbital so that it can make 4 bonds. And here we're going to hybridize just 2 of them into an sp, and then you're going to have these 2p orbitals left. Now those are higher in energy. So if we're going to do, our little diagram here, we'd have those guys, and we'd end up with 2 in the middle and 2 up here. So this is S and P, and this is SP, and those are just the p orbitals that are left. So these are unhybridized, and these are the hybridized orbitals. So we've got the hybridized orbitals, and we've got these guys. And so the carbon can form 4 bonds. It can form 1 bond with each of these orbitals. So what it does in acetylene is one of those sp hybrid orbitals overlaps with hydrogen, and the other overlaps and forms a sigma bond with carbon. This carbon has the 2 hybrid orbitals, one bonding with this carbon through a sigma bond, and the other doing a sigma bond with the hydrogen. There's 2 unhybridized p orbitals, one going this way and one going up and down. They're each half filled on both carbons, and so they're going to overlap side to side and form a pi bond here and a pi bond here. So we've got 2 pi bonds and 1 sigma bond between these 2 carbon atoms, and that's a triple bond. And it works out really nice because it's linear and it agrees with our experimental observations, and Vesper theory likes it too, and it's all good.
So what happens on the end of the hybrid result? It just attaches, another molecule attaches there? Or?
Nothing attaches to the hydrogens. Hydrogen can only form 1 bond.
So how does it connect to something else?
It won't. In order for this to connect to something else, you're going to have to break one of these pi bonds and have that orbital attached to something else. Yeah. Do you think there's rotation about a triple bond? Nope. No rotation around triple bonds. So any questions about those guys?
Are we going to need to know how that affects? Because how it affects polarity?
We don't really need to talk about polarity with hybrid orbitals because the Lewis theory works fine for predicting polarity of molecules.
Are we going to need to draw orbital diagrams for orbitals?
You may need to, we'll have to look at the test bank and see what kind of questions they have come up with. I don't remember from last year. It's important to understand the concept. Let's go back. It's important to understand these diagrams and what's going on here. That these are the atomic orbitals that we learned about when we studied quantum mechanics. We've got 3 p orbitals and an s orbital, and those can be hybridized in different combinations. And when you hybridize them, the level of the the energy of the hybridized orbitals are between the unhybridized. So this one comes up in energy, this one comes down. And if you think of averaging them, that makes sense. It also changes their shape, though. So if we take these two and combine them, we get two hybrid orbitals, and then these two just stay the same. Those are unhybridized. And so you can do these different combinations. You can have sp, sp2, or sp3. And those, the geometries that those give, when we look at these diagrams, this helps to explain why Vesper theory works. Vesper theory says the electrons are getting away from each other. But this is a deeper understanding of how and why they're doing that. How is that bond forming? And why is it in this geometry that we observe? When we get to the larger elements in the third period, we saw that we could have expanded octets. Well, what happens here is that we now are incorporating some of those d orbitals into this hybridization. So we can get sp3 with a d, and that's going to give us 5 equivalent orbitals, or we can get sp3d2, which will give us 6 equivalent or degenerate hybrid orbitals. The energies of the 3d orbitals are similar to the 3s and the 3p. So here's an example. Here's s, p, and d. So if we take the s and 3 p's and one of the d's, then we're going to get 5 sp3d orbitals, and the remaining d orbitals will stay there unhybridized. You're not going to find where you take an s and 1 p and some of the d's. You're going to take the s and as many p's as you need, and after you use up all the p's, then you can get into the d's. So those 5 orbitals will make this shape. Again, the second lobe is not shown. So that's a trigonal bipyramidal arrangement. And then you also have 4 unhybridized orbitals from the d's that are in there, and we're not going to draw those because they're crazy. So this is one of those molecules that violates the octet rule. Arsenic pentafluoride. So we've got 5 fluorine atoms around the arsenic. And if you look at arsenic in the periodic table, you'd say, oh, well, it has 5 valence electrons. It's got 2 in the 4s and 3 in the 4p. But that's not going to give it enough half-filled orbitals to overlap. And so those electrons are going to get bumped up into the d orbitals and hybridized together to make this wacky shape. So this is our friend, the bipyramid, the little girl with the tutu, right? So here she is standing straight up and down, and here's her tutu flaring out. Because girls like to do that, right? Twirly skirt. You can also take 2 d orbitals in there, and then you're going to get 6 equivalent orbitals, and that's where we get the octahedral shape.
Is
Yes?
there a particular reason why you wouldn't start hybridizing the 4s orbitals before the 3d?
That's a good question. Why not pull in the 4s orbitals before the 3d? The filling order for an atom has the 4s orbitals lower in energy than the 3d orbitals, and that's why the 4s fills first. But when we get into talking about things like this, it's going to stay with its quantum number. The reason that it does that is because of interactions between the electrons. But what we observe is that it's the 3s, the 3p, and the 3d, and the 4s doesn't come into it. I can't really give you a better explanation than that. But just based on orbital filling and energy levels, you might expect, well, why not the next energy level, right? The next one in energy. But it does the 3d instead. Yeah. So here's an example of that, sulfur hexafluoride. And so the sulfur is forming sigma bonds with 6 different fluorine atoms. So how do we know which hybridization scheme to use? Well, the rigorous method is that you would have to calculate it to find the lowest overall energy, and you would identify the degree and type of hybridization, and it would be a big involved thing. That's rigorous. We're going to go with good enough for Chem 1A. We're going to assign a hybridization scheme from the electron geometry of the interior atoms. So we're going to utilize Vesper theory to help us predict the hybridization scheme. Not 100% accurate, but good enough. And way easier, so we're going to go with that. Pardon me?
Remember after the test, the grade?
Yeah.
Good enough.
Good enough? So here are the geometries that we learned about today, right? Linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And this has to do with the number of electron groups. To figure out the hybridization, you're going to hybridize, for this one, you're going to hybridize 2 orbitals, S and P. For this one, you need 3 orbitals, the S and 2 of the P's. This one's got 4 S and 3 P orbitals. 5, well, you're going to have to get into the D's. So you've got the S, the P3, and a D. So a total of 5 orbitals hybridizing together to give you 5 hybrid orbitals, and 6, you'll have to dip into the D's even farther. Okay, so hopefully you see it makes sense. You've got S, 1 S, and 3 P's, and 5 D's. And you're going to start with the S, work your way through the P's, into the D's, and you're just going to take as many as you need to get the right number of groups. And you're going to decide this based on Vesper theory and looking at the Lewis structure. So, steps. Write the Lewis structure. Use Vesper theory to predict the electron geometry about the interior atom. Choose the correct hybridization for that atom based on the electron geometry. Sketch the molecule. It's best to start with one of the interior atoms and its orbitals, and then show how it overlaps with the appropriate orbitals on the terminal atoms, and then label the bonds. Pi or sigma, followed by the type of overlapping orbitals. So let's do an example. Use valence bond theory to write a hybridization and bonding scheme for carbon dioxide. Well, we need the Lewis structure. So we're going to have carbon and oxygens. And we've got 4 valence electrons from carbon. And we've got 2 times 6, 12 from the oxygens. We've got 16. And we've done this one several times. So I'm not going to spend too much time on it. But we're going to end up with this. 2, 4, 6, 8, 10, 12, 14, 16. Okay? Lewis structure. Now we're going to look at the central atom. How many electron groups are there? There's 2. The prediction is linear geometry, right? There's no lone pairs on the central atom. It's going to be linear. There's 2 groups. From 2 groups, that's what's going to tell us what hybridization the carbon has. What would we hybridize to get 2 equivalent hybrid orbitals? To get 2, we need 2. So just SP. If we do SP2, we'll end up with 3. So it's going to be SP hybridized. So let's put the carbon in here and put the oxygen over here and the oxygen over here. So the carbon is going to have an sp hybrid orbital going out that way and an sp hybrid orbital going out this way. And those are going to form sigma bonds. What do you think, what orbital do you think the oxygen is going to use to make those sigma bonds? The S or the P? Let's just draw a quick orbital diagram for oxygen. How many valence electrons does it have? 6. So 1, 2, 3, 4, 5, 6. Remember, we're assuming that these outside atoms are not hybridizing. So we're just looking at these two p orbitals are going to be what overlaps, right? So I'm going to draw them as p orbitals. The book does so much better job, doesn't it? My son does wire art. This is actually giving me an idea for a wire art sculpture with hybrid orbitals. He'd like that. So what kind of a bond is that? It's a sigma bond, and it's between what on the carbon? What kind of an orbital? sp. And what on the oxygen? Just a p, right? And that's the same as this guy over here. Everybody okay with that? Where does the double bond come from? The remaining p orbitals. Because with the carbon, we've got S and P, but there are also these other two p orbitals that weren't hybridized, and those are available as well. So what we get for the carbon is we've got sp hybrid, and then we've got the p unhybridized. And there's going to be one electron in each of these for carbon. So it's using one of its SPs over here and the other one over there. And now it's got two p orbitals left. So I've got color. I'm going to use color. So this carbon has an unhybridized p orbital that goes up and down, and another one that goes in and out of the page. You okay with that? Yeah. We used the p orbital that was going this way to hybridize with the s orbital, and that's how we got these two guys going in opposite directions. The remaining p orbitals are going to be perpendicular to these guys. So we've got this red one and the green one. The oxygen also has a p orbital left, right? We used one to make the sigma bond, and it's got another one. Okay, so this oxygen is going to use this one to overlap with that one and make a double bond. And this oxygen is going to use his up and down one to overlap with this p orbital from the carbon. So this red bond, is that sigma or pi? It's a pi bond. And what orbital on the carbon is involved? Just the p. And on the oxygen? Just the p. And this green bond is also a pi bond, and it's between a p orbital on the carbon and a p orbital on the oxygen, just like the other one. This is pointing to that guy. Are there orbitals on this oxygen that are not pictured? Yeah, there are. This other one would just have a lone pair in it. And this s orbital would have a lone pair in it. We're not going to worry about them. We're not going to draw the lone pairs. Those orbitals are there, but they're invisible. So look, I drew them with invisible ink. Do you see them? You're not supposed to. Okay? Any questions? You're like, I can't think of any right now, but I'm sure I'll have a bunch later. So this is one of those things that you have to practice doing, okay? Am I going to make you draw this on the exam? No, I'm not. It's a multiple choice exam. But there's something learning-wise that goes on in your brain when you work through and do something like this that helps you to understand the whole concept. And when you understand, then you can answer all kinds of questions about it. And there will be questions that get at, do you understand what's going on here? So do some of these at home. I don't remember if I assigned any in the homework, but you should always be working through the chapter and doing the examples in the text as you're going through. And so if you go to do the example and you're lost, that's when you go back on YouTube and watch this part of the lecture again. And the second or third time, it'll probably make a lot more sense. And that's where we're stopping for today.